Welcome everybody to episode 5 of Generally AI, an InfoQ podcast. The theme of the episode today is making waves, where we are going to talk about audio waves. The fun fact I wanted to start with is related to the loudness wars. Have you ever heard of the loudness wars, Anthony?
I don't believe I have. Tell me about it.
Okay, so I found this on Wikipedia. Apparently there is a trend of increasing audio levels in recorded music because every music producer wants their music to be really out there. So apparently every producer started finding ways to increase the maximum loudness of their music. And this really started with CDs, which apparently have a maximum loudness. But if you tweak the compression algorithm, you can make your music even louder. But it does mean that the fidelity of your music kind of dies out. So the loudness wars talks about, on Wikipedia, talks about this phenomena where music is getting louder and louder every year. But that, of course, also means that because of your compression, your details die out. And this is why Ian Shepherd organized the first Dynamic Range Day on April 21st to raise awareness that dynamic music sounds better.
Yeah, I have heard about people complaining about compression and how all music now has a lot of compression applied. And we actually probably could do a whole talk on that. But yeah, I'm not surprised it can cause distortion because that's essentially what it is.
Yeah, so apparently some people hear it. One thing which I found interesting, that Daft Punk's album Random Access Memories sounds great, and the engineer decided to use less compression on the project, and it won 5 Grammy Awards, including Best Engineered Album. And in the early 2020s, most major streaming services began normalizing audio by default. So I guess the problem of picking the loudest sound is gone, and now we just got to get our fidelity back.
So audio compression is certainly, I have heard of that, but I did not know that everyone was vying for the loudest song. So.
What I found interesting when I was looking at this on Wikipedia was that you can very clearly see that the old records, like the vinyl, then if you look at the audio wave, you can very clearly see that they're just trying to be as loud as possible the whole time instead of just being loud at specific parts of the song. So I guess this is why we should all switch back to vinyl.
So my fun fact is a similar theme. We're making a podcast, so we are recording our voices. And if you're like me, when you hear your own voice played back from a recording, you don't like it. I don't like the way my voice sounds. So why is that? Well, the fun fact is, and it's obvious when you think about it, when you hear your own voice, it partly is conducted through bone into your ear. So it sounds different, filtered through your skull, essentially, versus hearing it coming from a recording. So It doesn't sound like your voice at all.
I guess normally I at least hear my voice a lot lower in my head than it actually sounds.
Exactly. Right.
Yeah.
So the conducting it through the bones in your ears makes it sound deeper.
Yeah, I definitely sound better in my head than I sound on any recording.
Don't we all?
Don't we all? Welcome to Generally AI, an InfoQ podcast. As I said, the theme today is making waves. We are going to talk about audio waves. And what I don't really know today, Anthony, is who should go first, you or me?
Let me go first.
Yes,
if
please.
you don't mind. Because
yes,
we're going to have a history lesson. So we never know, of course, when a given listener is going to hear this podcast, but we're recording it right now. It's late 2023, November of 2023, actually. And Ridley Scott's new film, Napoleon, is in theaters. And I did go to see it. Now, regardless of what you think of the film or the subject matter, I feel like that's a good frame to start this discussion. Because this is a podcast, we're trying to tell a complex story in a limited amount of time. Just like Ridley Scott, I'm going to gloss over a few things and maybe not get the details. completely correctly, but I'm not going to deliberately make things up. So imagine you're a French mathematician living in the Napoleonic era, the turn of the 19th century. You're trying to solve differential equations. By the way, you probably knew this. Napoleon was supposedly quite good at math. There's a theorem attributed to him, although nowadays the consensus is he probably did not come up with it. But
Well,
there
what is
is
this theorem?
It's called the Napoleonic theorem. Sorry, Napoleon's theorem. It has to do with equilateral triangles constructed on the sides of a triangle.
Oh, that sounds completely different than what I expected.
Yeah. No, he was, well, of course, he was an artillery officer, so geometry and triangles were his thing. But the consensus is he got the idea from someone else. Anyway, I digress. So imagine you're a mathematician in this era. You're trying to solve a differential equation. In this case, a partial differential equation for heat transfer in a solid body, which is driven by a heat source or input.
As one does.
As one does. I guess they had a lot of free time. So there's no known general solution for this, but you do know two things. You know that a solution exists for sources that can be represented by a sine wave. And you also know a general property of differential equations of these types is that they are linear, which means that if you have an input function that can be represented as the sum of two or more functions, the solution is the sum of the solution for each of those.
Yeah.
That's called superposition. So anyway, this is the situation in the year 1807, where Napoleon is doing his Napoleon things. The mathematician was actually a real person named Joseph Fourier. Yeah. So he had this insight. He knew that there was a solution for sine waves or sinusoids. He also knew that the equation had the property of superposition. He realized if he could just figure out how to take other inputs and decompose them into a combination of sinusoids, then the problem was solved. And that's what he did. And that is the origin story of Fourier analysis.
Did he only invent the fact that these sinoids could be combined, or did he also figure out all the ways to calculate them?
Well, he figured out the way to calculate, given an arbitrary function, decompose it into a combination of sinusoids.
Okay, so it works for any arbitrary function.
Well, subject to certain constraints, but yes. Yeah. So, and there's actually variations on this. There's one way that works for periodic functions. There's one that works for arbitrary functions. And, I'm not sure what he actually came up with originally, but as with everything, he had the first idea, and people who've built on it have continued to credit him with it. So the mathematics is a little beyond the scope of what we want to do here. We need like a whiteboard and PowerPoints or charts, and it's calculus. So
yeah, I'm pretty sure that we will lose a lot of listeners if we start doing calculus lessons through a podcast.
Exactly. Yeah, and we'll leave that to the professionals at Khan Academy. So let me hit a few high points though. So in general, a sine wave or a sinusoid has a few parameters: the amplitude or height of the wave,
yeah,
the frequency or how fast it's going up and down, and the phase shift. Now that last one, if you visualize the wave plotted on an XY chart, you can think of the phase shift as moving it left or right along the x-axis.
Yeah.
Well, I said x-axis, but in fact, it's usually a function of time. So it would really be the t-axis. And I didn't even mention time at all, did I? But yes, it's also a function of time. But when you do Fourier analysis, time gets taken completely out of the equation, and everything becomes just a function of frequency. And this operation, changing from a function of time to a function of frequency, is called the Fourier transform. It transforms a function from what we call the time domain into the frequency domain. Remember, the function's domain is its possible input values. So the input to the function is no longer time, it's frequency.
So the input becomes frequency, and then the output becomes amplitude?
Yes, actually amplitude and phase. The value of the function is a combination of amplitude and phase. And so
what is phase then in this case?
remember with the sine wave, phase is shifting it left or right along the axis, right?
Okay.
So, well, how do you combine two numbers to get a single value? Well, use complex numbers. So maybe you remember the polar form of a complex number. If you thought calculus was going to lose us listeners, wait till we get into complex numbers.
Maybe
anyway,
I do remember it, but maybe
anyway,
not, and I'm not going to admit it.
Yeah, but anyway, with the complex number, the amplitude becomes the length. Remember, a complex number is like an arrow. It has a length and a direction it's pointing.
Yeah.
So the length is the amplitude, and the direction it points is the phase shift. And it turns out you can actually represent these using exponentials, or the number e, number 2.71828.
Yeah.
And you raise that to a complex exponent.
Yeah.
So what you get out of a Fourier transform is a function whose input is frequency, and the output is a complex number. It's e to the some complex exponent.
Yeah.
Okay, so the Fourier transform can take an arbitrary function of time and transform it into a function of frequency.
Yeah.
What that means is it's a linear composition of these exponentials. And because exponentials are solutions to a lot of differential equations, and because those differential equations have the property of superposition, that's why the Fourier transform is so useful. You can think of it as turning calculus into algebra. So maybe we won't lose as many people because we're now talking about algebra instead of calculus.
I'm sure a podcast about algebra is going to be a massive banger on Spotify.
I'm sure we're going to get a lot of streams. Fun fact, you get a half a penny per stream on Spotify.
I did not know that, but
that's what I've heard. Anyway, so why is this useful? So it turns calculus into algebra. So now you can solve those differential equations just using algebraic manipulation instead of having to do actual calculus. And there's another operation called the convolution, which is fairly complex. That just turns into multiplication. So you multiply your input function times some other function, and that's a convolution. You could think of convolution as when a signal goes through some system, like a filter, the system is performing convolution. So in other words, Fourier transform lets us do signal processing by using multiplication and division, or algebra.
Yeah, on the entire frequency domain at once, rather than on the individual wave.
Exactly. So and you can look at any particular frequency that you want because they're linearly independent, which is so that's actually a key assumption with a lot of these systems is that they are linear. That means that whatever happens at a certain frequency doesn't affect things happening at other frequencies. It turns out, of course, that's never true in reality, but for most engineering, you could pretend like certain things are true as long as you're okay with a little bit of an error there, like Ridley Scott shooting at the pyramids.
I don't know what's happening with Ridley Scott shooting at the pyramids, but
well, in the movie Napoleon's Army shoots cannons at the pyramids, which did not actually happen. But
okay, so
it looks cool to Ridley Scott.
Okay, I should really go watch this movie.
I just, I have to have an anchor, a frame to talk about things. Okay, so we've discussed the Fourier transform somewhat at a high level, from the time of Napoleon. Now we're going to fast forward 150 years or so to the middle of the 20th century, or the time of Oppenheimer.
Yeah.
So now we're in the age of computers and digital signal processing. And one key difference in this world compared to the time of Napoleon is sampling.
Yeah. What is sampling?
So, with a time domain signal, it's continuous, right? The sine wave goes up and down with no breaks.
Yes.
To get that into a computer, you have to take a snapshot of those values every so often.
Yeah.
And that's called sampling. And the key thing to remember, the rate at which you sample is called the sampling frequency. And that's very important.
Yeah.
Okay, but another thing, now that we're in the computer world, we're going to do a variation of the Fourier transform called the discrete Fourier transform, or DFT. First, you sample your signal. You collect some number of samples in. And remember, we're doing this at the sampling frequency. The DFT gives you a transform of those in samples from a time domain function into the frequency domain.
And what sampling frequency should I think about? What sampling frequency are we currently recording at?
Well, that's a great question. And I will bring that up in my list of caveats at the end.
Okay.
So what you get from the DFT, again, you get a set of complex numbers. And those represent the amplitude and phase of sinusoids, and they're sinusoids that are fractions of that sampling frequency. The first one, the zero component, is actually zero frequency, so it's a constant. Or in the electrical engineering world, we call it DC, or direct current. The second component, index 1, is the sampling frequency divided by n, the number of samples, and then you multiply, for each index after that, you multiply it by I. So the first one is 1 over n, or the sampling frequency over n. The second one is 2 times the sampling frequency over n, and so on. Now, it turns out there's a mathematical formula for calculating the DFT. And if you just did that calculation for each component, you're looking at a so-called big O complexity, which I think probably most of our podcast listeners will know this big O complexity for an algorithm. It's n squared.
Okay, but at the moment I am sampling at every possible, right? Like 1, 2, 3, 4, or am I already doing the quadratic numbers?
What do you mean?
You say I'm currently sampling at one times sampling frequency divided by n, 2 times sampling frequency divided by n.
That's the components, right? So
okay.
When you get an output, you get n complex numbers.
Okay.
And each one of them represents a sinusoid of a frequency from 0 to the sampling frequency divided by n, right? So
okay.
The last number you get out is the sampling, represents something of the sampling frequency. The middle number you get out is half the sampling frequency.
Yeah, got it. Okay, and so then the n for the O(n) squared, what is n in this case? Is it sampling frequency?
No, it's how many samples you collect.
Yeah, okay. And if that is squared, then that's quite a lot. Okay, that will grow quickly.
Right. Yes, you never want to see n squared if you can help it. So that was the problem. And in 1965, 2 mathematicians solved this problem. Their names were James Cooley and John Tukey. And they worked out a more efficient implementation that has complexity of n times the log of n, which is much better.
Way better.
Yeah. It turns out probably Gauss also came up with this like a couple hundred years ago, but didn't publish it. Again, as Gauss did. It turned out that Gauss invented everything, he just never published it. But anyway, by the way, this guy John Tukey is also credited with introducing the box plot in a textbook that he wrote in the 70s, and he's sometimes called the father of data science.
Oh, interesting. I never thought that someone was the first person to do a box plot.
Yeah, it's unclear if he's the first, but he introduced it into a textbook and made it really popular. Okay, so this implementation of the DFT, or discrete Fourier transform, this implementation was called the Fast Fourier Transform, or FFT. And it's probably one of the most influential and widely used signal processing algorithms today.
Nice.
Yeah, a couple of interesting things about the DFT in general and the FFT specifically. So you asked, what sampling frequency should you use?
Yes.
Well, it turns out that you need to use a frequency that's twice as high as the highest component frequency in your signal.
Okay.
So if you look at human speech, I don't even remember the numbers, but human speech, let's say the highest frequency is like 20 kilohertz, 20,000 cycles per second. You need to go at least double that. And if you're familiar with basic digital audio like compact discs, things like that, it's 44.1 kilohertz.
So perfect human voice plus a tiny bit for a piccolo.
I made up the number for human voice because it's about half. I picked half.
Yeah.
Of that.
Okay.
I don't actually know what it is, but your human hearing range does have a limit for most people, and it's probably about that.
Okay, so what you're saying is that my vinyl collection is worthless after all because I could have just listened to Spotify.
Well, I'm not going to get into that debate people do experiments sometimes with gear that audiophiles say is better, and with blind tests, a lot of times they can't tell the difference. So we did talk about how, nothing is ever linear. So probably there's distortion and artifacts introduced from sampling, but
Oh, yeah.
I don't know.
So is it then better to have a lot of bass in your songs or better to have a lot of high fidelity?
Probably the best thing is to have a good set of speakers, actually.
Okay.
But I digress. Okay, so sampling frequency needs to be twice as high as whatever the highest frequency in your signal is. So the other thing is the DFT assumes that your signal is periodic. This means that it assumes that it repeats itself at some frequency. So if again we talking of, I think you're going to talk about music. We know a note on a piano, like concert A, is 440 hertz.
Yeah.
That is the fundamental frequency. So that note, the signal of that repeats 440 times per second. Yeah. So the DFT assumes all its input is like that, and you've just given it, one period. If your signal's not actually periodic, the mathematics of the DFT assumes that you have applied a so-called window function.
Yeah.
And the output of the DFT is actually going to be a combination of the DFT of your real signal with the convolution of the window function's DFT applied. So it's actually kind of a mess. So long story short, the spectrum you get out is not quite exactly the real spectrum of the signal. It's
because
going to be,
you never know how much it repeats?
Yeah, it doesn't repeat, and you've pretended that it does. You've basically lied to the DFT, telling it's pretended. So the signal, the spectrum is going to be, it's called smeared.
Yeah.
You can actually apply other window functions besides just the chop. The rectangular window is what you do if you don't do anything. You can apply other window functions to try to get a little better response out of that. Again, I'm probably going to lose some people, so I won't go too deep into that. So that's the DFT in general. For the FFT specifically, there's a really weird result. I mentioned that the output of the DFT is a list of n numbers, just like you had an input of n numbers.
Yeah.
You have a list of n frequency components, spectrum components.
Yeah.
And they go from 0 to n-1, and those are, fractions of the sampling frequency.
Yeah.
With the FFT, the indices of these components are bit reversed. So what that means is that they're not in numeric order. Instead, you take the binary representation of the index and reverse the bits. So let me illustrate. Okay. Imagine that n is 4. So we have the index as 0, 1, 2, 3.
Yeah.
Index 0 is still 0. But the next index, 1, in binary, it's 0, 1.
Yeah.
You actually reverse that to 1, 0. Now that's actually index 2. So those two are, the second and third component are actually swapped.
Okay. And why do you do that?
That's the mathematics of the transform. That's how it's more efficient. Okay. That's the trade-off. Instead of being n squared, it's n log n, but the output is bit reversed.
This is like black magic with binary numbers.
It actually is. So the reason you can do n log n is you reuse some of the intermediate steps.
Yeah. Okay.
But so if you draw a diagram of it, it looks like this butterfly thing, and so things get swapped around, and it looks it's weird, but it gives you the answer n log n.
Nice.
But the output is essentially scrambled. So one interesting consequence of this is that back in the 1990s, where I actually did a lot of this in my time in academia, there was dedicated hardware devices, basically something like a GPU, but it was a digital signal processing hardware, dedicated hardware. It had a bit reversed addressing mode, so that you could transparently read the data out of memory in the correct order. So,
interesting.
Yeah. So so back then, so again, this is mid 90s, it was people doing this for serious, scientific and other instrumentation applications. They would try really hard to get the fastest, biggest FFT they could. And so just like with GPUs, there was dedicated hardware that could run these FFTs really fast.
Yeah, I actually think that for a lot of software applications, you can transform them to signal processing problems. And then you can use these onboard signal processors, which very little software engineers are ever doing. But I think that once you manage it, you're absolutely an optimization ninja.
Yeah. So again, I tried to throw the caveat out there that I was going to gloss over things and maybe not get everything completely right. The reason is I would be extremely embarrassed of any mistakes in this because my undergraduate and graduate education in electrical engineering, a good chunk of it was devoted to Fourier analysis and signal processing. So if I made mistakes, it's because time has erased some of that from my memory.
And we all know that when you're talking about time, you need to have as much details as your sampling frequency, right?
Exactly. Yeah. Yeah. We didn't even get into that. What happens if your sampling frequency is not high enough, you get what's called aliasing. So things that should look like high frequencies show up as low frequencies in the output of the DFT.
Yeah. Interesting.
Yeah. So that's my material.
I will add one fun fact to round off the fact that you started talking about Napoleon. Do you know where Jean-Baptiste Joseph Fourier is buried?
I do not.
Okay, so with everything in this podcast, I'm only doing research by actually going to the grave of the people who invented things. But so he is at the Cimetière du Père Lachaise in Paris.
Interesting.
And I actually went to his grave in 2014 when I was visiting or living in Paris. And I was trying to find a photo of me with the grave just for the show notes, but I couldn't find it. I could only find a photo I took of someone else who is on this graveyard, which is Jim Morrison. So I guess we can see that my my interest is more with old records than with people old mathematicians. But I did remember visiting the grave, so I did remember that he was buried there.
That's great. Hey, Jim Morrison kind of fits in there. Actually, Fourier went with Napoleon to Egypt.
Yeah, actually, I think that wasn't Fourier some kind of leader or governor of Cairo or something?
I don't know. He got left behind.
I only know that his gravestone looks a bit Egyptian or something. It's very weird.
Could be. Maybe they brought it back with them. Who knows? But yeah, so I completely forgot to add that to my notes that when Napoleon went to Egypt, he actually did not shoot the cannonballs at the pyramids, but he did, in fact, bring quite a few scientists with him to do some research there. So, and one of them was Fourier.
I think I have his grave, a photo of his grave in front of me, and there is some kind of Egyptian thing on the top. And actually, his face looks more like what Voldemort looks like in Harry Potter. But we should just say that they took the essential components of his face and they left out the details.
That's perhaps quite accurate.
Which is the weirdest joke I can ever make about Joseph Fourier.
Hey, it's Roland and Anthony here. I wanted to tell you about QCon London 2024. It is QCon's flagship international software development conference that takes place in the heart of London next April 8 to 10. I will be there, learning about senior practitioners' experiences and exploring their points of view on emerging trends and best practices across topics like software architecture, generative AI, platform engineering, observability, and secure software supply chains. Discover what your peers have learned, explore the techniques they are using, and learn about all the pitfalls to avoid. Learn more at QConLondon.com, and we really hope to see you there. Please say hi to me when you are.
The reason I was always excited about visiting or having visited the grave of Joseph Fourier is that I knew you could use this Fourier theory to recognize sound, like recognize songs. And I've always kind of consistently, by giving this as a fun fact to people, without really thinking of how does it actually work. So what I wanted to do with you is basically explain what I learned in the last couple of weeks of how I thought music recognition worked and how I was wrong. Does that sound good?
Sounds great. That's the best way to learn.
Yeah, because I thought, okay, well, Fourier theory can basically boil down any signal down to its individual components. So surely you just take a song and then take the entire song, calculate your individual song components, and then you can use it to reconstruct the song. But let's be honest, after what you just told me, that is going to sound absolutely terrible because most songs are not a very repeating signal, or they would be very boring songs. So people have to break it up. And I also think that it's actually, this is different than how humans recognize sounds. So humans are surprisingly good at recognizing sounds. And I figured I would do this with you, and also by preventing any kind of copyright strikes by me just humming the sound for you, and then you can recognize it. So if I say bum, 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 bum.
That's smoke on the water.
Yeah. And if I do bum, 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 bum.
Seven Nation Army.
Yeah. So you can
I'm
already.
good at this.
I took things which are very good for bass players to recognize. Those work well, right? And you can very quickly recognize them. But if I, for example, say tum 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 ta dum tum 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 ta dum tum.
Well, that's a good question. Wait, there's an extra note in Ice Ice Baby, so I didn't catch if it's Under Pressure or Ice Ice Baby, but
yeah, so
there's an extra note. There actually is an extra note in Ice Ice Baby.
So this is indeed interesting because Ice Ice Baby and Under Pressure have very similar things.
It's the same. He sampled it.
Yeah.
It's just there's an extra note.
I didn't even know there was an extra note. But for example, if I say dum dun 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 da da dun dun da 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 da.
Speed it.
Yeah. But if I would sing da 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 da.
Oh, transposed. We still know.
Yeah, it still beat it, right?
Yeah.
Like I at least didn't find the correct key for all these samples, and you still recognize them, which means that somehow humans are good at recognizing sounds, even if the key is wrong. And the fact that you recognized, for example, Beat It within, you recognize it very quickly. What I think is interesting is that Beat It by Michael Jackson is number 7 in the top list of most recognizable songs of all times.
What's number 1? Another One Bites the Dust.
No, not even that. So I only found this list, and it says Beat It is recognized in 2.8 seconds by most people.
Oh.
And number 1 seems to be Spice Girls Wannabe with 2.29 seconds. Yeah, I'll tell you what I want, really, really want. So tell me what you want, what you really, really want. Here is where I thought it started becoming weird, because number 2 was Lou Bega with Mambo number 5 in 2.48 seconds.
Is that playing the song or humming it?
Well, the thing is that it starts with, ladies and gentlemen, this is Mambo number 5.
Well, yeah, obviously it's what's the name of that song?
Yeah, so what I propose to you is that one day we just go to the studio and make a song called Most Recognizable Song, and we just start the song by Most Recognizable Song, and then we beat the record.
I have a teenage daughter, and a few years ago I found out that One Direction actually has a song called Best Song Ever.
Oh, smart.
But wait, it sounds exactly like Baba O'Reilly by The Who.
Oh. It is a pretty good song.
She played it for me. I said, we were listening to Spotify, and she played it for me. I said, go look up Baba O'Reilly by The Who. And she's like, oh, this is the same song.
Also, you were talking before, right? That the song "Ice Ice Baby" is sampling. There are way more songs nowadays which are just using samples of existing songs, which makes sound recognition harder because, of course, they are going to compose into the same spectrum.
True.
what I also found interesting is that, especially for us in Western music, it's very often about the progression. But sometimes you can also recognize songs just based on the instrument. Anyways, just to go back to what does this have to do with Fourier? As I said, I initially thought, oh, you can probably represent the entire song as individual sound waves. And I never tried this, but I figured it would probably just sound very bad. And I also think that if you would try to recognize an entire song based on just those sound waves, it would probably also not work and probably be a mess.
Mm-hmm.
But there are a lot of apps nowadays which are good at this, even despite noise in the background. And some apps you can even hum a song to and it will recognize it.
Oh, nice.
And I think the app which most people are using is Shazam. So let me start with Shazam fun facts. When do you think Shazam started?
Ooh, I know it's been around a while. So I don't know, 2005, 2008.
Yeah, so you probably think it's from 2008 because that's when it became an app. But Shazam has been around since the year 2000, when it used to be a phone number.
Oh, interesting. Really?
Like when you were at the bar, you could use your mobile phone to call this service. You would just hold your phone in the air for 30 seconds, and then it would send you a text afterwards with what the song is.
I can't imagine that worked very well. It's from a bar. That must have been really challenging.
Yeah, well, I mean, you have a mobile phone, you can recognize songs, which I think is insane. They are located in London, by the way. And they actually wrote a paper in 2003 where they were describing how they were able to recognize 2 million songs.
Wow.
Which is already a lot. It was purchased by Apple in 2018 for $400 million.
Wow.
There are other services. So the others I found is Hum to Search from Google. So Google supports that. Okay. And apparently on some Android phones, you can have a now playing function, which sounds insane. I unfortunately don't have one of those phones. But the entire time, your phone is listening to, is there music in the background? And if there's music, it tells you what music is playing.
Well, we already knew they were listening to us, but I guess...
Here's the insane thing. They are actually doing this on device.
That's amazing.
Yeah, so they have a really interesting paper describing how they do this on device, because you need to do this on device, fast, while keeping your battery power in mind. And you have to have this entire music database.
On device?
On device, yeah.
That's bonkers.
Yeah, it is, because they have a way to get all these songs down to as little bytes as possible for the recognition.
Send me the link to that paper.
I will send you the link to that paper. But let me first start giving you some secrets to this music recognition, because maybe then you can implement it yourself.
Sure.
And I think the first thing I already talked about is, instead of taking the entire song at once, you split the music into parts, into snippets, which are individually recognized.
Yes.
So for each snippet, you try to get a match for individual songs. Mm-hmm. So for each snippet, you have basically a list with from what song it could be. And then already guessing the song, if you have a couple of snippets which you're not very sure of yet, you try to match those snippets to those songs as well.
I see.
So you start with a couple of snippets you are relatively sure of, and then you try to fill in the remaining snippets to see if they can actually fit. So it's basically starting with a puzzle. You know, if you have a puzzle and you know what the pattern is probably going to be, you start with very clear pieces and then you can try to fill in the rest. And if that works, I mean, now this puzzle analogy breaks down, because if that works, you can actually find the correct box.
Well, I mean, you could think about it as a sequence matching.
Yeah,
in a way.
Indeed. You are matching a sequence. The second thing I was initially thinking of is, okay, well, you just take the waves and then you take this image, basically, the spectrogram, and then you match that entire thing. So whenever videos or explanations would say, oh, you just take a fingerprint, I would be a bit annoyed, because I was like, oh, but you got a spectrogram. Isn't that the entire fingerprint? No, probably not, because that thing is massive. So people take representations or hashes of this spectrogram. And I found multiple approaches which worked over the years. I think the Shazam paper talks about I'm now trying to make you visualize this, but if you have the spectrogram and you see all those waves and hotspots going around over your time period, you can, instead of having all these details and all the sound waves, you can get the most dominant frequency at each time period. So, for example, every 100 milliseconds or every 10 milliseconds, you take the most dominant frequency at that time point. That gives you a lot of dots. And then you can start doing constellation matching to find the song with that constellation.
Ah, interesting.
Yeah, and I think one thing which is especially cool here is that this is important if the frequency can change. Like when I am humming songs to you, I don't know exactly if I'm on key for the songs I'm playing. And this is, so in this case, the fact that you're doing constellation matching solves that problem. The other thing I found, by the way, is that you as a musician probably know that if I go one octave up, I am doubling the frequency of my sound. So if I would sing ha, that doubles the frequency of the sound wave my mouth is producing. Ha, ha. Fun fact. But we as humans perceive that as the same note. So maybe I was humming a low A and then later I'm humming a high A. But we perceive this as the same note. You know, when you're saying happy birthday and you're suddenly you have to say happy birthday, dear Anthony. Sometimes you will automatically in your brain just go lower instead of higher because you can't hit a high note. That's when your brain is deciding to just take the same note but then lower instead of higher. And our brain interprets it as the same note. So I also saw that some papers had a way of encoding frequencies which are changing by an octave, basically in the same way to account for this problem.
Ah, interesting. So another thing, again, you probably know this, but sometimes we have a hard time determining the exact pitch, you know, A versus A flat, but we can detect intervals, like we can distinguish intervals correctly. That's how we can, you know, I can pick the same melody even though you're singing it at a different, humming it at a different key.
Yeah, so what you're describing is how most humans are interpreting songs, which is by relative pitch.
Yes.
Do you know how many people have absolute pitch?
Not very many. My son says that Charlie Puth does, but I don't know beyond him.
Yeah, so apparently it's 1 in 10,000 people have absolute pitch. So they know exactly if they hear a sound, what frequency it is on, what note it is.
Yeah, it's amazing.
Yeah, apparently these people are sometimes having a harder time learning music or recognizing melodies because it is not exactly the same melody.
I can believe that.
And this is what I tell myself whenever I'm having issues playing music, is that maybe there's a chance I have absolute pitch.
Oh, is that it? I thought you were going to say that's the upside. You know, the fact that I'm terrible at singing, that's a good thing because then I can appreciate good stuff other people can.
Yeah, no, I always tell myself if I'm having an issue recognizing or playing music, I think, oh, maybe I secretly have absolute pitch. I just didn't notice it yet.
It's possible.
Yeah, I don't think so. I think I'm just very bad at music. So the thing for this matching the snippets and calculating the fingerprint, nowadays people use neural networks. This has also been taken over by neural networks. And the loss function you can use here is basically you say that two snippets are matching if they are just like a few hundred milliseconds apart. So you can take a tiny piece of a song, take the same piece of a song, or take the same song, but then 100 milliseconds shifted. And you tell the neural network, these are actually the same snippets.
Okay.
You should recognize it's the same thing. And that gives you a fingerprint. That gives you this ID, this hash, which you need to recognize songs. And that brings me to the last problem, which I addressed, and that is that some songs sound a lot like other songs, and some songs sound very unique.
Mm-hmm.
But you still want to have a function to recognize the song as fast as possible, despite these differences, right? So issues you could have here are, for example, songs with loads of samples, maybe some generic house songs, which all just start with a random beat, and you just don't know what's happening. And one paper I found, which I found super interesting, is a paper which did a density-based distance function. So basically, they changed the threshold for picking a songs based on how many songs there are in the cluster where you are searching.
Oh, interesting.
So if you would start with the dum 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 dum, it would probably pick up, it is in this cluster of songs. But because there are so many songs which have this baseline, I'm not picking the exact song yet until I'm really, really sure and I gathered enough samples, I gathered a long enough string of patterns which match.
Nice. That makes sense.
Yeah.
Here's a random thought. We often hear of lawsuits about this song is actually a copy of some other song. So we talked about Ice Ice Baby, but maybe you've heard, this happened to Led Zeppelin with Stairway to Heaven. It happened with, there was a pop song that was considered a ripoff of a Marvin Gaye song. Anyway, has anybody ever thought of using one of these song recognition algorithms to basically figure out, well, yeah, they're actually not, yes, they are very similar, or no, they're not actually really that similar. That would take the subjectiveness out of it.
Yeah, it still seems to be really about the objectiveness, unfortunately, because it's really also about how many notes do you have in a row, and also what is the chance that you already heard a song seems to play into it.
Yeah. Blurred Lines, that was the song.
Blurred Lines.
Robin Thicke, but it was supposedly a ripoff of a Marvin Gaye song.
Oh, interesting.
Anyway. I have another cool FFT story related to absolute pitch. So when I alluded to doing this sort of work in graduate school, perhaps you've heard of a musical instrument called the theremin.
Yes.
If you've ever watched a 1950s sci-fi movie that goes, woo, that's probably a theremin.
Yes.
And what it consists of a simple oscillator. It's controlled by the proximity of your hand to an antenna.
Yeah.
You move your hand closer, the pitch goes up. Woo! You move it away, it goes down. Ooh. When I was working in the robotics lab, a good friend of mine, his name, by the way, is Jason Burrill, and he runs Theremin World website, thereminworld.com.
If they are looking to sponsor a podcast, our podcast would be a great one.
He started this website in like 1994 or 95, I forget. But,
interesting.
So yeah. So anyway, he was a theremin enthusiast, and so he said, wouldn't it be cool if we could make the robot play the theremin?
Yeah.
And I said, that would be extremely cool. I said, here's what we do. So we plug the theremin into the computer. So the audio goes into the computer. It's sampled. We do an FFT. The FFT gives us the frequency component, and it's a very simple waveform. It's basically you get big spike, little spike, smaller spikes, right? So we just find that biggest spike. That's the frequency or the note that we're playing. And if we move the robot arm closer, it goes up. We move it away, it goes down. It's servoing. Right? Yeah. So we have a target frequency, which we had a MIDI keyboard. You press a button and it tells here's the frequency we want. And you just servo. It's literally we used a proportional controller at first, but you can do PID control to make it a little smoother. But literally just move closer, move further away. And we wrote a paper on that, and that was one of my favorite papers to do in grad school.
Nice. That sounds quite fun. We once tried to build a theremin ourselves, but then instead of using an antenna, we used a, infrared sensors for distance.
Oh, so proximity. Yeah.
Proximity. But then you could use the entire room for your theremin. So we did that at some art festival. We put that down. People had fun with it.
Oh, that's cool.
I don't know if I'm proud of it or not, but we had a lot of fun building it.
Well, the same with this paper. It was one of the even more fun was, we had the basic, servoing. One of the other researchers said, well, you need some vibrato, and we literally just added sinusoids to the joints, so to make the hand go wom, 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 wom. And it was comical. People would get a kick out of that because the arm would just go like that, and it sounded pretty cool, actually.
I know that sometimes at IROS, this conference for robotics, they have a music and robots competition. So sometimes people are indeed handing in things like this. You would like it. I was really impressed with some of the performances some people put down with their robots.
Where is the next IROS?
I don't know.
I'll have to check that out. I may have to show up for that. That'd be cool. We'll do a live podcast from there. Didn't you do a podcast from there?
Yeah, I recorded a podcast at IROS, or no, ICRA this year.
Oh, it was ICRA. Yeah, right.
And the next one seems to be in Abu Dhabi, October 14 till 18, 2024.
Be a little out of my way, but
it is quite far.
You get around a lot. So.
But naturally, Anthony, you and I are going to meet each other at QCon London, right?
Is it London? I don't know if I can get to London. I was thinking I might go to New York. Are you going to be? You'll be in London.
Listener, you would totally have to go to QCon London, right?
If I have a chance, I will go.
If any listener of this podcast was listening to this right now, you would totally have to go to QCon London, April 8 to 10 in London.
It's on the calendar.
It's on the calendar. Anyways, let's go to Words of Wisdom. What did we learn in this podcast? And did you learn anything yourself recently?
Well, I mean, obviously learned a lot about Napoleon and Fourier. I had forgotten that they worked together. I was not aware that Google had this app that could do the song identification on device. That's pretty remarkable.
In the background, continuously. Yeah. That's the insane thing with the whole database stored on your phone. It's really cool.
I don't know how they do it.
I completely forgot that this Fourier transformations are entirely based on e to the power imaginary numbers. That's really cool.
Yeah, that's for those who have not learned this. Euler, mathematician, he had a formula. E to the ix is equal to sine of x plus I times the sine of x. So that's how that works. So imaginary exponents on or complex exponents on E give you sinusoids.
Yeah, really interesting. Anything you learned in your personal life last week?
Oh no, gosh. So it was Thanksgiving here in the United States. So it should be a time for reflection, but unfortunately, probably didn't do as much of that as I should have.
Okay, I already started preparing for the next episode, which we tell you later about. But I went to Greenwich, which is an area here of London, and they have the prime meridian line, the prime meridian of the world, which is longitude 0. So every place on the Earth is measured in terms of its angle east or west from this specific line. And since 1884, the prime meridian has served as a reference point for Greenwich Mean Time. And the thing I was very confused about is that I came to this place and I saw all these signs for, oh, this is this line we used in this year. Oh, this is the line we used in that year.
Really?
Yeah, because I was very confused. I found like 5 different lines of where point 0 is, longitude 0. I asked them, it turns out that these were all the places where people set up their telescopes. So really the line where someone set up the telescope to do all the measurements from was the line. So there is actually a telescope like 5 meters away from this prime meridian, from where they do all the measurements.
I thought there was an observatory there. I guess I didn't consider that they might be moving the telescope.
Well, it's every time someone makes a better telescope, they put it a couple of meters to the west. So that's why the line always moved a couple of meters to the west.
This is going to mess things up quite a bit.
Well, yeah, I will tell you, I can tell you next time that it's even more confusing, because if you check your GPS at the prime meridian, it is not at longitude 0, but 112.5 meters away from it.
Interesting.
But if people want to know more about that,
I can't wait.
We can tell them in the next episode, which will be called Lost and Found.
Awesome.
Anyways, if people enjoyed this podcast, the way I get all my podcast information is from friends telling me about it. So why not make someone happy and make their day by recommending them this podcast? You can also make our day by liking this podcast. Thank you, Anthony Elford, for joining.
Thanks, Roland. This is fun as always.
And thank you, listeners, for listening to this episode. This was Generally AI, an InfoQ podcast.
I wonder if Google recognizes this tune.